Hello, this is Shankara Avancha. I am presenting on protecting bare metal embedded systems with privilege overlays. The authors on the original article are Abraham A. Clements from Purdue University and Sandia National Laboratories, Naif Saleh Al Makdoub from Purdue University, Khalid S. Saab from Georgia Institute of Technology, Prashant Srivatsava, Jinku Ku, Saurabh Bachchi, Matthias Peyer are from Purdue University. This paper was originally presented at 2017 IEEE Symposium on Security and Privacy. The link to the original article is provided here. We'll first discuss what the embedded systems are, the threat model that we are getting prepared for, list our assumptions. We will understand the current architecture, review the solution in the light of its design and implementation, discuss the evaluation provided by the authors. An embedded system is a computer system that is a combination of computer processor, computer memory, and input-output peripheral devices that has a dedicated function within a larger mechanical or electrical system. It is embedded as part of a complete device, often including electrical or electronic hardware and mechanical parts. Because an embedded system typically controls physical operations of the machine that it is embedded within, it often has real-time computing constraints. Embedded systems are everywhere. There are about 9 billion embedded processors. About 98% of all microprocessors manufactured are used in embedded systems. With the rise of the Internet of Things, the number of embedded devices have grown exponentially. These things include like utility soft meters, smart locks, smart TVs. Many of these devices are low cost with software running directly on the hardware known as bare metal systems. In such systems, the applications run as privileged low-level software with direct access to the processor and peripherals without going through intervening operating system software layers. These bare metal systems satisfy strict runtime guarantees on extremely constrained software platforms with few KBs of memory, few MBs of flash, and low CPU speed to minimize power and cost constraints. Embedded systems largely lack protection against code injection, control flow hijack, and data corruption attacks, whereas desktop systems employ many defense against these attacks such as data execution prevention (DEP), stack protections, separate return stacks, and safe stack, diversification, and so on. Consequently, attacks on desktop systems became harder and often highly program dependent. Achieving known security properties from desktop systems on embedded system poses fundamental design challenges. First, a single program is responsible for hardware configuration, input, output, and application design. Thus, the program must be allowed to access all hardware resources and to execute all instructions. This causes a fundamental tension with the best practice, security practices which require restricting access to some resources. Second, bare metal systems have strict constraints on runtime, energy usage, and memory usage. This requires all protections to be lightweight across these dimensions. Third, embedded systems are purpose-built devices. For example, a register in one system may unlock a lock, while on a different system it may control an LED used for debugging. Clearly, the former is a security-sensitive operation, while the latter is not. Such application-specific requirements should be supported in a manner that does not require the developer to make intrusive changes within their application code. To address all these challenges, the authors of the paper developed epoxy, embedded privilege overlay on X hardware with Y software, a compiler that brings both generic and system-specific protections to bare metal applications. This compiler adds additional paths to the traditional LLVM cross-compiler flow. These passes add protection against code injection, control flow hijack, and data corruption attacks and direct manipulation of I/O. Central to their design is a lightweight privilege overlay, which provides solution to the problem of allowing the program developer to assume access to all instructions and all memory by restrict access at runtime. To do this, epoxy reduces execution privileges of the entire application. Then, using static analysis, only instructions requiring elevated privileges are added to the privilege overlay to enable privileges just prior to their execution. Epoxy draws its inputs from a security configuration file, thus decouples the implementation of security decisions from application design and achieves all security protections without any code modification. In adapting fine-grained diversification techniques, epoxy leverages unique aspects of bare metal system. Specifically, all memory is dedicated to a single application and the maximum memory requirements are determined a priority. This enables the amount of unused memory to be calculated and used to increase diversification entropy. Epoxy then adapts the protection to safe stack, enabling strong stack protection within the constraints of bare metal systems. The prototype implementation of epoxy supports the ARM v7M architecture, which includes popular Cortex M3, M4, M7 microcontrollers. Their techniques are general and supported to and should be applicable for any microprocessor that supports at least two modes of execution and has an MPU. Threat model. For the attacker, we assume a remote attacker with knowledge of generic memory corruption vulnerability, that is, application running on the embedded system itself is buggy but not malicious. The goal of the attacker is to either achieve code execution, corrupt specific data, or directly manipulate security critical outputs of a system by sending data into specific IO pins. We assume the attacker exploits a write what where vulnerability, that is, one which allows the attacker to write any data to any memory location that he or she wants. The attacker may have obtained the vulnerability through a variety of means, example source code analysis or reverse engineering the binary that runs on different device and identifying security flaws in it. We also assume that the attacker does not have access to the specific instance of the firmware running the target device. Assumptions of the target system. First, it is running a single bare metal application which utilizes a single stack and has no restrictions on the memory, address, peripherals, or registers that it can access or instructions that it can execute. This is the standard mode of execution of applications on bare metal systems. Second, we require the microcontroller to support at least two execution privilege levels and have a means to enforce access controls on memory for these privilege levels. These access controls include making regions of memory as read, write, or execute. Typically, an MPU provides this capability on a microcontroller. We will review the architecture information that is needed to understand the attack vectors and the defense mechanism in epoxy. Bare metal systems have low-level access to hardware. This enables an attacker with a read, what, where vulnerability to manipulate the system in ways that are unavailable to applications on the desktop systems. Defense strategies must consider these attack avenues and constraints of hardware availability to mitigate threats. The authors had worked on ARM v7M architecture, which is implemented in ARM Cortex M3, 4, or 7 microcontrollers. The general techniques are applicable to other architectures subject to the assumption we have discussed earlier. Memory map. In our threat model, the attacker has a write what where vulnerability that can be used to write to any memory address. Therefore, it is essential to understand the memory layout of the system. Note that these systems use a single unified memory space. A representative map is provided to here for the illustration. At the very bottom, we have the region is the aliased memory region. When an access is made to the aliased region, the access is fulfilled by accessing physical memory that is aliased, which could be in the internal RAM, internal RAM, internal flash, or external memory. The alias itself is specified through a hardware configuration register. Thus, memory mapped by the alias region is addressable by two addresses, its default address and the address to the alias region. This implies that the defender has to configure identical permissions for the alias memory region and the actual memory region that it points to. A common peripheral contains a memory mapped register that sets the physical memory address to the alias region. A defender must protect both the registers that control which memory is aliased in addition to the physical and alias memory location. Moving up the address space, we come to the internal flash. This is flash memory that is allocated inside the microcontroller. On ARM v7M devices, it ranges in size from couple of KBs to couple of MBs. The program code and read-only data are usually stored here. If no permissions are enforced, an attacker may directly manipulate the code. Address space layout randomization is not applied in practice, and the same binary is loaded on all devices, which enables code reuse attacks like ROP. Above the flash in RAM, which holds the heap stack and global stack, common size for this is like 1 KB or a couple of 100 KBs. It's usually much smaller than the flash area. By default, this area is rewrite and execute enabled, making it vulnerable to code injunction attacks. Additionally, the stack employs no protection and thus is vulnerable to stack smashing attacks, which can override return addresses and hijack the control flow of the application. Finally, here if you see here SCB, right, this is the system control block. This is a set of memory mapped registers defined by ARM and present in every ARM v7M microcontroller. It controls the MPU configuration, input vector location, system reset, and interrupt priorities. Since SCB contains the MPU configuration registers, an attacker can disable the MPU simply by writing a 0 to the lowest bit of the MPU controller register located at the address, a specific address. These indicate that the SCB region is critical from a security standpoint. The execution privilege modes. ARM v7M processors can execute in different privilege modes. However, they only support two modes, privileged and unprivileged. In the current default mode of operation, the entire application executes in privileged mode, which means that all privileged instructions and all memory accesses are allowed. Thus, we cannot indiscriminately reduce the privilege level of the application for fear of breaking the application's functionality. Once privileges are reduced, the only way to elevate privilege is through an exception. All exceptions execute in privileged mode and software can invoke an exception by executing an SVC instruction. This same machine mechanism used to create system calls in traditional voice. The memory processing unit. ARMv7M devices have a memory processing unit or MPU, which can be used to set read, write, or execute permissions on regions of the physical memory. The MPU is similar to the MMU, but it does not provide virtual memory addressing. In effect, the MPU adds an access control layer over the physical memory, but memory is still addressed by its physical addresses. In summary, current bare metal system design exposes a large attack surface. Memory corruption, code injection, control flow hijack attaches, right to security critical but system-specific I/O, and modification of registers crucial to system operations such as SCB and MPU configurations. Next, we will discuss the design of their solution, epoxy, which resolves this tension by using privilege overlays along with various diversification techniques to remove the attack surface. Okay. Epoxy's goal is to apply system-specific protection to the bare metal applications. This requires meeting several requirements. One, protection must be flexible, as protected areas vary from system to system. The compiler must enable the enforcement of policies that protect against malicious code injection, code reuse attacks, global data corruption, and direct manipulation of I/O. Enforcement of policies must satisfy the non-functional constraints, runtime energy usage, and memory usage should not be specifically higher than the baseline in secure execution. The protections should not cause the application developers to make changes to the development workflow and ideally would involve no application code changes. Epoxy's design components, we have like 4 components to apply protections to the bare metal systems while achieving the above 4 goals. These are one, access control. Access controls which limit the use of specific instructions and access to specific memory locations. Access controls are used to protect against code injection attacks and defend against direct manipulation of I/O. Access controls specify the read, write, and execute permissions for each memory location and instructions which can be executed for a given execution mode. And the next one is the novel idea of privilege overlay, which imposes the access control on the unmodified applications. They maintained the developer's assumption of access to all instructions and memory locations by using a technique they call privilege overlay. This technique identifies all instructions and memory accesses which are restricted by the access controls, referred to as restricted operations, and elevates just these instructions. Conceptually, this is like overlaying the original program with a mask which elevates just those instructions which require privileged mode. Next one is the identifying restricted operations. To identify restricted operations, they utilize static analysis and optionally source code annotations by the developer. They use 2 analyses to identify restricted operations, one for restricted instructions and a second for identifying restricted memory accesses. The next one they used is an adapted safe stack. Epoxy defends against control flow hijacking attack by employing safe stack. Safe stack is a protection mechanism that uses static analysis to move local variables which may be used in an unsafe manner to separate a unsafe stack. Basically, a variable is unsafe if it may access memory out of bounds or if it escapes the current function. The last component in the design is the diversification techniques, which utilize all available memory. the implementation, the access control. They developed a prototype implementation of epoxy, building an L on LLVM, low-level virtual machine. The implementation access controls are specified using a template. The template consists of a set of regions that map to MPU region configurations. Due to current hardware restrictions, a maximum of 8 regions are supported. Their basic template uses 5 regions as shown in this table. Region 0 encodes default permissions. Using region 0 ensures all other regions override these permissions. They then use the highest regions and work down to assign permissions to ensure that the appropriate permissions are enforced. Privilege overlays. The privilege overlay mechanism are implemented using an LLVM pass. To alleviate privileges, two components are used. They are a privilege requester and a request handler. Requests are made to the handler by adding code which performs the operations around restricted operations as shown in this algorithm 1. This code saves the execution state and executes a SVC to elevate privileges. The selected instructions are then executed in privilege mode, often by a code sequence that drops privileges by setting the 0 bit to the control register. Safe stack and diversification. The safe stack in Epoxy extends and modifies the safe stack implemented in LLVM 3.9. Their changes enable support for ARM v7m architecture. They change the stack to grow up and use a global variable to store the unsafe stack pointer. Stack offsets are applied with global data randomization. Global data randomization is applied using a compiler pass, and it takes the amount of unused RAM as a parameter, which is then randomly split into 5 groups. These groups specify how much memory can be used in each of the following regions, like stack offset, data region, BSS region, unsafe stack offset, and unused. Evaluation. The evaluation has been done with respect to different benchmarking features. The benchmark performance evaluation, this is used to measure the effects of techniques on runtime and energy. They have used BEEB benchmarks. BEEBS benchmarks are collection of applications from MIBench, WSET, DSP Stone benchmarks. They are designed and selected to measure execution performance and energy consumption under a variety of computational loads. The application performance evaluation. To understand the overall effects of realistic applications, they use 3 representatives of IoT applications. Their first program, like the pin lock, which simulates a simple IoT device like a door lock. It requires a 4-digit PIN to be entered on a serial port. Upon reception of the PIN in hashed and using SHA-1 and compared to a pre-computed hash. If the hashes match, an LED is turned on indicating the system is unlocked. If an incorrect PIN is received, the user is prompted to try again. In this application, the IO is restricted to privileged mode only. Thus, each time the lock is unlocked, privileged execution must first be obtained. This demonstrates Epoxy's ability to apply application-specific access controls. Security evaluation. Epoxy enables application of WXRX in proven protection against code injection and is fundamental for other protections. WXR mechanism also protects against attacks which attempts to bypass or disable WXRX by manipulating system registers using a write what where vulnerability. Comparison to free routes. So they have compared epoxy to FreeRTOS MPU which does not provide WXRX or code reuse defense. Conclusion: bare metal rarely employs any security protections, and the authors have presented epoxy and LLVM based embedded compiler using privileged overlay techniques to address this challenge. And using this technique, operations requiring privileged execution are identified, and only those operations executed are executed in the privileged mode. This provides basis for implementing code integrity, adapted control flow hijacking defense, and protection over sensitive IO. These are all applied. So I thank all the authors of the original paper for the research effort and sharing this with the engineering community. And I thank all of you for taking time to view this presentation with utmost interest. And I also invite you to share your feedback and post any questions on this subject on the appropriate discussion forum on PSR. Thank you. Thanks a lot.